Welcome to the introductory video about wave interference. We're going to look at that and also what is called superposition. The introduction here is kind of neat, and it has two very interesting simulations in it that you could run when you were reading this after class. But we're going to look at some different things in here about how waves interact when they're in the same medium. We know, of course, that their speed is controlled by that medium, so it's not that that's changing. So we're going to do this a little bit out of order of the book, but if you remember last time we had this simulation and we have the wheel that makes the wave, and if I pulse it, it just moves right down based on the medium. Well, we did this with no end, so that pulse just continues on forever. We could also change it from a pulse to being a wave by changing this to oscillate, and you can see that that wave also goes on forever. It just goes out the window. Well, what if we did the same pulse but we had a fixed end? Alright, if we pulse it, you can see that's moving down, alright, and we're going to let it play, and it reflects. Ooh, did you see it flip sides? Let's reset that and give that again. It comes down and it's on the top, it reflects and comes on the bottom. That is called reversing it or flipping it, or however you want to indicate that it is flipped on the other side of the string. Now we're using a transverse wave, but we could do this also with a longitudinal wave and we'd see the same thing. As we hit the other end, that's another fixed end, so you can see it just keeps flipping back and forth. If we reset this, and now rather than an infinite end, we have a loose end. Watch what happens here at the loose end. Did you notice? Let's reset it. The pulse reflects, but it stays on the same side. It doesn't invert. When we had the fixed end and we sent that pulse, it inverted. It flipped on the other side. Alright? So that's one difference. Alright, so what if rather than just one pulse, we had two pulses? So I'm going to leave this as I'm going to actually change this to a loose end. So remember here what happens is the pulse reflects and it stays on the same side. I'm going to send a pulse, and then I'm going to send a second pulse, and you can see it started to reflect here. What I want you to see, I think I'll try that again. I'm going to send a pulse, then I'm going to send another pulse. Watch as they come together. What superposition means is they occupy the same space. So as they come together, here's our two pulses. As they come together, the two pulses add together, and when they occupy, I wish I could go back one step. As they occupy that exact same space, they're actually right on top of each other, they're twice as high, but then they keep going and they go right through each other. Now it looked kind of like maybe they reflected off each other, and in fact if we let this play, we see all sorts of weirdness going on. Hold on, and then they're back. Let's do it again. Here we go. Pulse, pulse, reflect, join big, and then they keep going. That's a little harder to see, so let's give it a fixed end. Now remember, what happens with a fixed end is the pulse inverts. It changes sides. So here we're going to have a pulse, and then I'm going to send another one, and now they're coming at each other from opposite sides. There they are. They're going to add together. They're going into superposition. They add together, and it's perfectly flat. But the question is, do they bounce off, or do they travel through? And if you notice, our one that was on the bottom continued through on the bottom. The pulses travel through each other. They do not bounce off each other. So that's what's happening. That's called interference. When they're in superposition, they interfere with each other. But notice they don't destroy the wave. They just add together when they're in that position. Alright, so we're going to move on to something called a standing wave. And what's happening with a standing wave is when you have a wave, now remember, our wave, here we have an oscillation. So we have a wave here. If we do that wave from a fixed end, that wave, and I'm going to reset it, that wave is going to invert when it hits that fixed end. So I'm going to change this to manual, pulse, reset, so I can start to oscillate it. When it gets down there to that end, it's going to invert. So let's watch. It comes in below, comes back out above. Well, when that wave starts to add to the wave that's coming, and they add together perfectly. I'm trying to get a nice balance here. Let's see. I had it going before. We're going to hit reset on that. I think it's around 34. We get we get that idea of resonance. We get a standing wave where they're adding together perfectly and they're moving in opposite directions, and so they have opposite amplitudes. You get this perfect wave that's called a standing wave, and it looks like it's standing there. Here's a video clip that shows a nice one on a string. You'll notice some things about it, like a wavelength is from, we know what a wavelength is, it's from identical point to identical point. So the wavelength stays fixed because it stays at the same point the whole time. And also, I have some other videos of these, but they're too long to include here. If we want to, we can watch them next time that we're in class. So here's that video showing a cool standing wave on a string. Now, one of the other neat things about standing waves is this is how we get stringed instruments to make music. Their strings vibrate with a standing wave, and that's talked about here in part 7 about harmonics. There's some vocab here: the fundamental frequency, the harmonic, and there's some other vocab also that we just didn't talk about right now with standing waves, where the part that doesn't move is called a node, and the part that has maximum displacement, maximum motion, is called an antinode. It is where they completely cancel out, they're called nodes, and where they completely 100% add together and increase, they are called antinodes. The next section I wanted to talk about was section 10 here, which is how we get music from different types of pipes also. And I have a really neat video on this that we're going to show in a minute. It's something you definitely shouldn't do at home, but I'll show that in a minute. I thought it was kind of cool. I was talking to Mr. Shippen this morning, and he's doing this with his honors geometry students, making music, because what happens in a tube is you set up a standing wave within the tube, and you have, if the end of the tube is open, you get what's called an antinode, maximum displacement, and if it's closed, there's a node at that place. Now, I've got these really neat things called boom whackers, which again, when we're back in class, if you ask and you're interested, we can play with those and look at the difference between if that standing wave starts with a node at the end or an antinode at the end. The video you're about to see is kind of dangerous. It does it with propane, but look at the pattern of the flames at the top. So here's that video.
272.
All right, that was definitely something I would never want you to do at home. But if you notice, that pattern at the top is the pattern of the nodes and antinodes within the pipe, because there's that standing wave, which is actually, we show it as a transverse wave, but it's a longitudinal wave. So it's creating areas of high and low pressure, which directly correspond to the high and low pressure of the propane in there, and therefore a high pressure produces a high flame and a low pressure produces a low flame. And so it's a great visualization of it. All right, last couple of topics, but they're really cool. There's one about what happens if the path from sound sources are different. Well, you get interference. Sometimes you get constructive interference, which is what creates those antinodes, the maximum displacement, and sometimes you get destructive interference, which is what creates the more of a node or a lessening of the amplitude. All of this, remember, we're playing with the amplitude, not with the wavelength or the frequency, because that is determined by the speed and by the medium. So there is another cool demonstration we can do in class with two speakers and demonstrate path length for you. Let's go on to our last topic, which is called beats, beat frequency. It's here in section 17. So I'm going to let you watch this short little 30-second video which demonstrates beat frequency. Make sure you do have your volume turned up nice and high. So here you go. All right, so what's happening with a beat frequency is you have two different waves that are in superposition, i.e. occupying the same space, and they are slightly different frequencies. Thus, they are in a regular pattern, interfering with each other constructively and destructively, and you get this overriding amplitude, overriding wave that causes the sounds to increase or decrease. That was the wah, wah, wah you hear. And sometimes I've heard that like in our theater, especially before they redid it. I do have a neat demo of this in class, but I also found this video that shows it really well using a smartphone app to look at the different frequencies. It's not the individual waves, but the overriding, like you see here in this final graph. And you're going to hear a surging in the sound. Alright, so that's all of the sections in this reading, and in class we will do some interactives, and if you have any questions, please respond to the last one in this, and I will see you in class.